Hi, in this video we're going to look at how we calculate type 1 and type 2 errors when working with a Poisson distribution. Now, as we dealt with in binomial distributions, Poisson distributions are distributions that deal with discrete data, and so we have to treat them differently to the way that we deal with normal distributions. And just as we did with the binomial distributions, we're going to figure out where our acceptance or rejection zones are, what the probability of being in those particular zones are, once we've been given a particular value that will decide where that acceptance zone or rejection zone starts. So, unlike the normal distributions where they'll say calculate this to a significance level of 10% or 5% or whatever the case might be, in the discrete data, they're going to tell you our rejection zone is going to be, if they're greater than this or if they're less than that, one of those values will be given to you. So let's deal with a problem and work our way through that. So here's a problem based in ecology. Plants on sand dunes are found to be on average at at 10 per square meter. After a dry season, there's concern that the plants in the area have been badly affected. In a randomly selected 1 meter plot, 4 plants are counted. If X is the random variable for counting the number of plants in a particular zone, then if X is greater than 4, it will be decided that the weather has had no effect. So there they've told you where our acceptance and rejection zones are going to be. If the number of plants is greater than 4, then we will say that the null hypothesis has not been disproved, that we can accept the null hypothesis. If it's less than 4, then less than or equal to 4, because they say if X is greater than 4. If it's less than or equal to 4, then it will be in the rejection zone and we will reject our null hypothesis. So, first of all, we need to set up what the null and alternate hypotheses are. So, to begin with, our null hypothesis is going to be that lambda is equal to 10 plants per square meter. Now, we think that the weather has affected this, has reduced that down. So in other words, our alternate hypothesis is going to be that lambda is less than 10 plants per square meter. And remember, we've got X as being the number of plants. It's a Poisson distribution. Lambda is equal to 10 plants per square meter. And we're going to reject if X is less than or equal to 4, given that lambda is equal to 10. So, firstly, we need to try and figure out what is the type 1 error, the probability of the type 1 error. And that means we need to figure out what is the percentage of being in the rejection zone. Type 1 error is all about being in the rejection zone. So what is the probability in this case of being in our rejection zone? Being in the rejection zone will be the probability where X is less than or equal to 4. And I need to just make a little rider there. This is, of course, given that lambda is equal to 10. So if I want to work this out, this is going to be the probability that X is equal to 4 plus the probability that X is equal to 3 plus the probability that X is equal to 2 plus the probability that X is equal to 1 plus the probability that X is equal to 0. And if I go and figure that out, this is going to be e to the power minus 10 times 10 to the power 4 over 4 factorial plus e to the minus 10 times 10 cubed over 3 factorial plus plus e to the minus 10 times 10 squared over 2 factorial plus e to the minus 10 times 10 to the power 1 over 1 factorial plus e to the minus 10 times 10 to the power 0 over 0 factorial. And if you go and key all of that into your calculator, you're going to come up with a number over here that says 0.0293. So therefore, the probability of a type 1 error is going to equal 2.93%. So there's the probability of the type 1 error, the probability of rejecting a true hypothesis. The next thing that we're going to look at is what is the probability of getting a type 2 error. If in fact the mean number of plants was 8 per square meter, not 10 as they originally felt. Now remember, type 2 errors, they must always give you the true value of the mean or the proportion, or in this case lambda. So we know that our acceptance zone is going to be if x is greater than 4. And that acceptance zone is going to stay. So we want to know what is the probability of being in the acceptance zone. So in other words, what's the probability of being that x is greater than 4? However, now this is going to be determined when lambda is equal to 8, not equal to 10. And so this will be the probability of 1 minus the probability that x is less than or equal to 4, given that lambda is equal to 8. And so that's going to be 1 minus, let's just put this down again. This time it's going to be e, there's a big bracket around there because it's going to be all of these, e to the minus 8 times 8 to the power 4 over 4 factorial plus e to the minus 8 times 8 cubed over 3 factorial plus e to the minus 8 times 8 squared over 2 factorial plus e to the minus 8 to the power 1 over 1 factorial plus e to the minus 8 times, not e, times 8 to the 0 over 0 factorial. Okay, a bit tedious writing all of that out, but they do need to see it. And then all you need to do is crunch that into your calculator, and you're going to come up with a value that is 0.9003. So therefore, the probability of a type 2 error is going to equal 90.03%, much higher. Now, I didn't deal with this sort of problem in the binomial distribution, but I'm going to deal with it here. And the process we follow through is going to be, will apply to the binomial as well as to the Poisson. And that's basically when we look to approximate our problem using a normal rather than using the binomial or the Poisson distribution. So take a look at this problem. The average number of flaws per 100 meter of yarn produced by a machine is 7. So in every 100 meters of yarn, there are on average 7 mistakes. This is like a pattern or something like that, so that's being printed onto some material. The machine is serviced, and the number of flaws in the first 300 meters is 27. We're expecting it to be at 21. So it looks like it has increased. Carry out a two-tailed test at 5% to see if the number of flaws has changed. Now, by giving you this significance level at 5% would be an indicator to you that you're going to have to approximate the Poisson distribution, because they're giving you a precise value for the significance level of the test. So what do we know so far? We know that lambda is going to be 7 floors per 100 meters. However, we're also told from the machine, once it's been serviced, that there are 27 floors per 300 meters. Now we're expecting, if we were working with 300 meters, for there to be 21 floors per 300 meters. That would be the situation if the machine had not been serviced, if it carried on working the way it was before. Now, because lambda is greater than 15, I can approximate with the normal. And that's going to make my calculations quicker and easier to work with. So if you remember the approximation of Poisson, if lambda is equal to 21 per 300 meters, then we're going to say our expected value mu, that's going to be 21, and our value of our variance, so sigma squared, that's also going to be a 21. And so we can say that our faults can be modeled by a normal distribution. Mu is equal to 21, and sigma squared is going to equal 21 as well. Our variance is going to be 21. Now they're asking you to test at a significance level that's at 5%. And what we need to figure out now, is this going to be one-tailed or two-tailed? And here we need to read the question carefully. See if the average number of floors has changed. They're not asking has it gone up, they're not asking has it gone down, they're asking has it changed. And so this is going to be a two-tailed test that we need to work with. So if it's two-tailed, remember our curve is going to have 95% here. So this value is going to be at 97.5, this value is going to be at 2.5, and so our z-score is going to be at 97.5, which is 1.96. So we've got our z-score. We now want to find what is the probability that z is greater than or equal to 27. And this is where we need to be careful, because we're dealing with discrete data originally, although we're approximating it now with a normal. So if we think about it, we've got our columns happening here. We want to be greater than or equal to the block that's at 27. So in other words, we're talking about the probability that z is greater than or equal to 26.5. We want to go all the way over there. Remember, 27 is in the middle, so we're going to go from the extreme left-hand side of that block all the way over. So in other words, we're talking the probability that z is greater than or equal to 26.5 minus, and the mean we said was 21, and we're going to divide this by the standard deviation, which in this case is going to be the square root of 21. And if you go and crunch that into your calculator, we're looking at the probability that z is greater than 1.20, blah, 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 blah. In other words, it's going to be 1 minus the probability that z is less than 1.20, blah, blah, blah. And since our z-score is less than our z-score at 5%, or 2.5% for the right-hand side, our value is going to be within the acceptance zone. So therefore 27 is in the acceptance zone, and so therefore we're going to accept the null hypothesis. Right, if x represents the number of flaws, what would be the value of x for the null hypothesis to be rejected? So in other words, we want to figure out where are our critical values. So remember, we've got our normal distribution. We said that our mean in the middle was at 21. We said our standard deviation was the square root of 21. And what we want to find is, where is the rejection zone when we're working at a significance level of 5%. So in other words, our rejection zone is going to give us 2.5% on this side and 2.5% on that side. So in other words, we're talking about 97.5% over here, and our Z score for 97.5 is 1.96. So that's going to be a crucial value for us to work with. So if we want to figure out our confidence interval is going to be given by our mean, which is 21, plus or minus 1.96 times by the variance, the standard deviation rather, divided by the square root of 21. And if we do that and put that into our calculator, well, the lower bound is going to be at 11.51, and our upper bound is going to be at 30.38. But now remember, we're dealing with number of flaws, we're dealing with discrete values. So in other words, we're going to reject if x is less than or equal to 11, and we're going to reject if x is greater than or equal to 31. And so that gives us the values for our acceptance zone, and by continuation, the values for our rejection zone. So I hope this makes sense to you. What you now need to do is to go and practice some of these. So go and look at the exercises that have been allocated. Goodbye.